Hello, students. Today we're going to be working on finding the volume of a solid that is created by rotating a region around an axis that it's not completely attached to. And the method that we'll use for this is an extension of the disk method. It's called the washer method. And a washer is just a disk with a hole in it. And I would encourage you to look at the PDF versions of these notes so that you can see, for example, the finished product of this first problem and get a little bit better idea of what this washer method is all about. But today we'll be looking at this first example. We're going to rotate a region that's bounded by a semicircle, the square root of 25 minus x squared, and a horizontal line y equals 3 around the x-axis. So you can see right here is the x-axis, and we definitely have a region that is not connected to that x-axis. So what's created is a hole, and so we're going to define two radius values. The first one we're going to call the outer radius. This outer radius is measured from the axis of revolution up to and through the region. So it's the region and the hole. And for this problem, that would be defined by the square root of 25 minus x squared, that semicircular region. And then we'll also define what I call an inner radius. And in that case, it's just the hole. Again, you measure from the axis of revolution and stop at the beginning of the region. And that's the hole that's created. That in this problem is going to be defined by 3. Now, something that you have to be careful about as you set up your volume equation, we're doing the volume by doing pi r squared h again, but doing that with integration. So pi, this time we're going to take the two radius values and subtract them. The other thing you have to be careful about is noting those points of intersection. So the x values would go from -4 to +4. And we'll take that outer radius, the square root of 25 minus x squared, and remember to square that. Then we'll subtract from that the inner radius. Remember to square that. And then you get the height by using dx, where we make that infinitely small. So there's our setup. We'll do a little bit to simplify. So pi times the integral from -4 to 4. When we square the square root goes away. And then we'll get 25 minus x squared minus 9 dx. We can simplify one more time. So pi times the integral from -4 to +4. 25 minus 9 gives us 16, so 16 minus x squared. So then we'll actually do the integration. That gives us volume equals pi times, and the integral of 16 is 16x, minus the integral of x squared, which is x to the third power, over 3. And this is evaluated from -4 to +4. And since I'm running out of space, I'll just trust that you can do the fundamental theorem of calculus, plugging in your 4 first, and then plugging in the -4. And your final answer for this volume is 256 pi over 3. For our second example, we're looking at a region that we will be revolving around the y-axis. I wanted you to see a vertical revolution. Remember that whenever we revolve around a vertical axis, then we integrate with respect to y. So that means we need to solve our equations for x. So that's actually the first thing I'm going to do. I'm going to take that top equation and now it already is y equals x, but I'm just going to turn it around to x equals y. And then our second equation is y equals x to the third. And so if we take the third root of each side, we would get x equals the third root of y. Probably for our purposes, it would be easier to think of as x equals y to the 1/3 power. And so then we're going to look at this inner and outer radius idea. So the axis of revolution is the y-axis. We want to look at a radius that would go all the way through the region, including the hole. So from the axis of revolution all the way through the region, and that would be described by our cube root, so y to the 1/3 power. And then the inner radius on this one goes from the axis of revolution to the beginning of the region. And so that would be our line. And so that is y. And then I want to be sure that you understand we are integrating along the y-axis. So we want to pay attention to these y values from 0 to 1 as we set up our volume equation. So volume is going to equal pi times the integral from 0 to 1 along the y-axis. We're taking the outer radius and squaring that, so y to the 1/3 squared. And we're going to subtract from that. We'll take the inner radius, which is just y, and squaring that, and then dy. So our volume is going to equal pi times the integral from 0 to 1. Well, when you square with fraction exponents, you just multiply the exponents. So that's going to be y to the 2/3 power minus y squared dy. So now we can start doing the actual integration. So volume will equal pi times, and we'll be plugging, or excuse me, we'll be doing 2/3 and adding 3/3 to that. So that's going to be 5/3 power over 5/3. That's going to become 3/5. So 3/5 y to the 5/3 power minus, and then for your other one, y to the third over 3. This is evaluated from 0 to 1. And I'm again going to let you plug in the 1 and simplify. And that's going to give you a final answer of a volume 4 pi over 15. 4 pi over 15. Again, this one was rotated around the y-axis. I want to show you a third example where we take a region and rotate it around a horizontal axis that is not the x-axis. So this time we'll take the shaded region you see here and rotate it around the horizontal line y equals 8. So as we think about the outer radius that is created, we want to be sure that you're understanding we draw that line from the axis of revolution all the way through the region. And that region, the end of that region is at the x-axis. Well, the length of that radius, this outer radius, is 8. And that's one of the boundaries that you see here listed on the left. And then we look at the inner radius. So again, we want to start with the axis of revolution and draw that radius segment to the beginning of the region. All right, now it's tempting to say that that would just be the parabola, but actually the parabola is measured from the x-axis up. So going from 8 down, we would actually have to take 8 and subtract the parabola. So that outer radius is 8 minus 2x squared. So we're going to set up our volume equation, pi times the integral from, we want to use the x boundaries since we're rotating around a horizontal. And so we'll be going 0 to 2. The outer radius is 8, squaring that, minus the inner radius, 8 minus 2x squared, and squaring that. So there's our volume equation. We'll simplify. So volume equals pi times the integral from 0 to 2. And 8 squared is 64 minus, and then we have a binomial that we'll have to square. So 64 minus 32x squared plus 4x to the fourth. And then we can combine some like terms, distribute the minus sign. So volume would equal, or pi times the integral 0 to 2. We have 64 minus 64, that's going to cancel. The minus negative 32x squared will become positive 32x squared. And then the minus sign will also distribute to make minus 4x to the fourth dx. So now we're ready to do the antiderivative, do the integration. So volume would equal pi times, for 32x squared, we would have 32x to the third over 3 minus, and then for 4x to the fourth, we get 4x to the fifth over 5. This is evaluated from 0 to 2. And once again, I'm going to just give you that final answer. After you plug in the 2 and the 0, you would get 896 pi over 15 for that volume. 896 pi over 15. All right, for our last example, we're going to look at a region that is formed by two curves. The first curve is x equals y squared. And then the blue curve, the second curve, is x equals the square root of y. And notice that we're going to rotate this around the vertical line, x equals 1. So when we look at the outer radius for this, we want to start at the axis of revolution and draw all the way through the region to where the region stops. And so this will be the axis 1 minus the red curve, which is y squared. Notice that it's vertical, so we had to solve it for x. And then we'll look at the inner radius, which is just the hole from the axis of revolution to the beginning of the region. And so again, that would be the axis 1 minus the blue curve, which is the square root of y. So our volume equation will be volume equals pi times the integral. We want to go along the y-axis, so from 0 to 1. And we'll take that outer radius, 1 minus y squared, square that, minus the inner radius, 1 minus the square root of y, and square that, dy. So volume would equal pi times the integral from 0 to 1. After multiplying this out, we would have 1 minus 2y to the second plus y to the fourth minus, and then 1 minus 2 square root y plus y. And for our next step, we will combine some like terms. So volume would equal pi times the integral from 0 to 1. Your ones actually cancel. So we'll have minus 2y to the second plus y to the fourth plus 2, and I'm going to write the square root as y to the 1/2, and then minus y. And this is what we will finally do the integration for. So volume would equal pi times, so for negative 2y squared, we'll have negative 2y to the third over 3. For y to the fourth, we'll have plus y to the fifth over 5. For the plus 2, we'll have y to the 3/2, and that's over 3/2. So when we simplify that, we will get 4/3 y to the 3/2, and then minus y squared over 2. This is evaluated from 0 to 1. And so for our final answer, we'll have a volume equaling 11 pi over 30. Volume equals 11 pi over 30. So again, take a look at the PDF for some more detailed instructions on solving these, and good luck with your assignment.